Good. Then let's start with the first talk by Michael Romano. You can start sharing your screen if you want.
Okay.
Excellent. So Michael will talk about the role of major mergers in the galaxy mass assembly as revealed by the ALPINE survey. Please, Michael, the floor is yours.
Okay, can you see the full screen?
No, yes, now we can.
Okay, perfect. Okay, thank you for the introduction. So, hello everyone. My name is Michael Romano and I'm a postdoc at the National Center for Nuclear Research in Warsaw. So before starting, I would like to thank the organizer for giving me the opportunity to present my work, which is on the role of major mergers in the galaxy mass assembly as revealed by the ALPINE survey. So in the next slides, I will first introduce the scientific context of this work, and then I will provide a brief introduction of the ALPINE project and a description of the ALMA data I have used in my analysis. And then I will describe the method used to spot mergers in ALPINE, and I will go through the major results of my work. And finally, we'll provide just some conclusions and future prospects. So we know that galaxies assemble their stellar mass mainly in two distinct ways. On the one hand, they can grow by forming new stars from cold gas, which could be either accreted in their surrounding or that is already within the galaxies. But alternatively, they can grow by merging with other sources in their local environment. And in particular, major mergers can increase the stellar mass of galaxies up to a factor of 2. And they are defined based on this quantity mu, which is the ratio between the primary and secondary components of the merger in terms of their stellar mass. And so typically, if this ratio is smaller than 4, we consider the merger as major. And so in this work, I focused on the study of the merging process through the ALPINE data to understand its contribution to the mass buildup of galaxies. And usually two principal ways are used to spot mergers at a given epoch, which are the count of galaxy pairs close in the sky and the analysis of morphological disturbances. And through this, it is possible to obtain an estimate of the fraction of mergers. And by assuming a certain merger timescale, we can obtain the corresponding merger rate. And many works have investigated the incidence of mergers across cosmic time. But there are still few observational constraints on the merger fraction in the very early universe that are also hampered by the use of photometric redshifts or by the small statistics. But with ALPINE, we have provided the first constraint on the merger fraction at redshift 5 based on spectroscopic redshifts and on the morphokinematic information provided by the C2 emission. And so let me spend just a few words on ALPINE. ALPINE stands for ALMA Large Program to Investigate C+ at Early Times. This project was led by Olivier Lefebvre, and it carried out 70 hours of C2 and continuum observations in ALMA band 7 for a sample of 180 normal star-forming galaxies drawn from the Cosmos and extended Chandra-Deep Field South fields. And this ensured to each target an impressive multi-wavelength coverage. All these sources have spectroscopic redshifts between 4.4 and 5.9, with a gap in between to avoid prominent atmospheric absorption feature. And all the targets are main sequence galaxies with star formation rate from 10 to hundreds of solar masses per year and stellar masses between 10 to the 9, 10 to the 11 solar masses. And you can see here the distribution of galaxies in the two ALPINE redshift bins and their position along the main sequence at redshift 5. About the C2 emission, as you can see from this sketch of a typical star-forming galaxy at redshift 5, this line is one of the strongest lines in the far-infrared regime, and it is the major coolant of the interstellar medium. The bulk of its emission originates from photodissociation regions, possibly tracing the formation of new stars. And also it is poorly affected by dust extinction than optical tracers. So it offers, let's say, a perfect chance to reveal the presence of mergers with dusty components that would otherwise be partially or completely obscured in the optical bands. And finally, the continuum surrounding this line lies close to the peak of the far-infrared dust emission, constraining the obscure star formation. And so for all these reasons, the C2 emission can provide important information on a variety of ISM properties. And thanks to ALMA, we have now an easy access to this line for high redshift star-forming galaxies up to the epoch of reionization and beyond. And so the ALPINE data are basically in the form of 3D data cubes that can be inspected at different wavelengths and positions to retrieve both imaging and spectroscopic information. Here, the black histogram represents the spectrum of one of the ALPINE galaxy. And at each frequency, we can see the emission from the galaxy through these channel maps, which are a resolution of 25 kilometers per second. And in this case, we can also see multiple components, both in the maps and in the spectrum, highlighting the presence of a possible ongoing merger between two galaxies. And so by inspecting each data cube and by assuming a threshold of 3.5 in signal to noise, we can divide the ALPINE sample in 75 C2 detections and 43 non-detections. And you can see in this image the C2 intensity maps of the 75 ALPINE detections, where you can also appreciate how different is the morphology from one galaxy to the other. For instance, you can see that some sources are more compact or extended than the other, while some shows clear signs of merging activity. And so starting from this data, we selected our merger candidates among the 75 ALPINE detections by inspecting the moment maps, integrated spectra, and multi-wavelength observations. Indeed, in case of mergers, we expect the presence of two or more separated components in the optical images or in the moment maps and position velocity diagrams, but even a complex behavior in the channel maps and in the C2 spectra. And this is an example of our merging systems. Here, the two top panels show the HST and ultravista KS band emission. We overlaid the C2 and optical contours in cyan and yellow, respectively. And these are the velocity and velocity dispersion maps. In particular, in the velocity map, we plot the major and minor axes used to compute the corresponding position velocity diagram. And finally, the bottom panel displays the C2 spectrum in black, extracted within the 3 sigma contours of the Mon-Zero map. And here, the green and blue lines represent the possible components of the merger, whose sum is given by the red line. And in this example, you can clearly see the two merging components, both in the moment maps and in the major PV diagram, represented by these two clumps of emission. And so we take advantage of all this information to define some selection criteria to produce the final sample of mergers in ALPINE. So in this figure, we plot the difference in velocity between the merger components as a function of the projected distance for all the merger candidates shown in the legend. Here, the gray region shows the sources which are more secure to be mergers because they have a delta V smaller than 500 kilometers per second, which is a good threshold for gravitationally bound systems. And also they have a distance larger than the typical C2 size of a galaxy at this redshift, that is about 2.1 kiloparsec. And so, but we also consider these sources on the left because they could be distinct galaxies merging together, but with small projected distance because in the final stage of merging. And this is justified by these two panels, which show that the individual sizes of the minor and major components of the candidate mergers are comparable with the sizes of the other ALPINE galaxies that are represented by these light squares in the background. And so in the end, we decided to include all these systems in the final sample that is composed of 23 mergers out of 75 C2 detections. And so we define the merger fraction in this way as the ratio between the total number of mergers after correcting for completeness and the number of ALPINE galaxies in the considered redshift bin. And we obtain a significant fraction of mergers of about 40%, which is shown by these blue stars in the two ALPINE redshift bins, and which represent the first constraint on the merger fraction from C2 emission at this epoch. And we then compare this fraction with a collection of other data at different redshifts from the literature, selected to have a stellar mass comparable to that of the ALPINE galaxies. And we fit this data to provide a cosmic evolution of the merger fraction using this function here. And here we show the best fit in black and the corresponding uncertainty in gray. And basically we found a rapid increase from the local universe to higher redshift with a possible peak at redshift 3 and a slow decrease towards earlier epochs. And we also compared these results to those from the Eagle hydrodynamical simulation, finding a very good agreement, even though this simulation only reaches redshift 4. And so we just extrapolate this trend to higher redshifts. And then we translate the major fraction into a merger rate like this, where C is the fraction of close pairs that will eventually merge into a single system in after a typical timescale T. And we also assume these three different timescale prescriptions that are usually considered in the literature. So in this figure, the solid lines show the best fitting fraction to our data combined with those at lower redshift, assuming these timescales. And you can see that the three curves show a steep increase from the local universe up to redshift 1, and then they differ significantly at higher redshifts. And we also show the results from different cosmological simulations as dashed lines, and found that to reconcile most of them with the observations, we need a strong nonlinear dependence of the merger timescale with redshift. However, there are many factors that affect these results, like the probability of merging or the selection criteria used for the close pairs, but most of all, the adopted timescale prescription. And all these uncertainties, let's say, are also highlighted by the average number of mergers a galaxy undergo between redshift 6 and 0. And this is obtained just by integrating the merger rate over time. So from this figure, it is clear that the average number of mergers computed with the Kitzbichler and Jiang prescriptions, these two curves here, is very low, possibly leading to less than a single merger event per galaxy during its whole lifetime. But on the other hand, if we assume the rapidly evolving timescale by Schneider, then the number of mergers increases significantly, reaching 8 events per galaxy at the present day.
3 minutes.
And finally, we provide an estimate of the average mass accreted per major merger and per unit time and volume to cosmic time. So in particular, we define this mass accretion rate density in this way, where mu is the average mass ratio of the sample, and gamma is the merger rate density, that is the previously defined merger rate per unit volume. And this is a very useful quantity, as it can be directly compared with the star formation rate density that is reported here in red from Madao and Dickinson 2014. And so again, we show our results as solid curves for different merger timescales, and we also report the latest results from ALPINE for the star formation rate density by Kusanova 2020. And also in the bottom panel, you can see the ratio between the merger and star formation quantities. And so we found that assuming the slightly redshift dependent merger timescale by Kitzbichler and Jiang, major mergers contribute less than 10% to the galaxy mass assembly at all redshifts. On the other hand, by considering the Schneider timescale, a larger contribution of mergers in the early universe is in place, which becomes also comparable to that provided by star formation at redshift 6. And so we cannot exclude that major mergers may have a significant role in the galaxy mass assembly in the early universe. But of course, we have to deal with the large uncertainties caused by the choice of the merger timescale. And so to conclude, in this work, we have investigated the role of major mergers in the stellar mass assembly of galaxies from the high redshift to the local universe. To do that, we have exploited the ALMA C2 observations as part of the ALPINE survey. We have used for the first time the morphokinematic information provided by C2 to obtain an estimate of the fraction of mergers at redshift 5. And also because the properties of the C2 line, the fraction we obtain is robust against the presence of dust and highlights a significant merging activity in the universe. And then we converted this merger fraction into a merger rate and found that the population of mergers provides, in general, a smaller contribution to the galaxy mass assembly than in situ star formation at all epochs, although the two processes start to converge at high redshift depending on the merger timescale used. And so this suggests that the amount of mass added to galaxies through major mergers may be directly comparable to that added by in situ star formation of this epoch. But further investigation is needed in order to, let's say, confirm these results. And a number of things could be implemented in this respect. For example, we could increase the sample size with more observations at high redshift in order to have a larger statistics. But we can also increase the resolution to reach a better selection and characterization of close pairs in the early universe. Or we could go to higher redshift and see if the bending of the cosmic evolution of the merger fraction still holds. And of course, many other things can be done to improve these results. And so this was my last slide, and thank you for your attention. And if you have any questions or advice, I will be happy to discuss with you. Thank you.
Thank you, Michael, for your nice talk. Do we have any questions?
So there are no questions in the chat for the moment, but while people are thinking, so I wanted to ask something. So Alpine mainly focuses on C++, and I understand that this is a very key line and very useful, but so among these other things to do in the future, so are there plans of observing other molecules that could help, or it's C++ right now with the instruments that we have the only possible thing to really
so I think that at high redshift, maybe C+ is the best choice we can do. You know, as I said, it's a very strong line, and we can use the morphological and kinematic information that is accessible with it. But maybe to lower redshift, we can use other tracers, for example, I don't know, UV and optical tracers like Lyman alpha or O2 emission line. There are many other studies that have used these tracers to spot mergers. So yes, I think that in the local universe or in general at lower redshift, it can be done with these other tracers, but at high redshift, this start to be complicated. So I think C2 is the best choice right now.
There is another question from the chat if I can. So yeah, and if there is time. So,
yes.
So they ask, what's your plan to increase the sample statistics?
Yeah, well, we can think to do some proposal with the new ALMA cycle, for example, but of course, increase the statistic with ALMA could be very expensive from the timing point of view. So another, let's say, another choice could be to use ALMA observation in synergies with, for example, JWST, because JWST will have, let's say, larger resolution, high resolution that we can use to spot mergers in the very high redshift universe. So maybe, of course, we have to do another proposal with JWST, but we can use the synergies between these two powerful telescopes to increase the sample. There are also other programs that are currently making observations at high redshift, like, for example, the Rebels project at redshift larger than Alpine, or I know about Crystal that made high resolution observations. But of course, we don't have access to this data, so.
Okay, thank you very much, Michael. There's more questions, but we will post them in the Slack. I see you already stopped.